Okay, I got interruption in my internet connection and I'm continuing here from this slide. I hope that the other part of the recording is already in the recording. Blackboard collaborate file with this half-time for the reaction. If it's a first order, then the half-time, it has a simple formula of T half 0.693 divided by K. As long as the value for K is given, we can do the calculation for half-time. And also, if the value for K is given and is per second, that means it's a first order reaction. How do we recognize that? You basically either have to memorize or you say rate. The unit for rate is always mole per second, okay, equals K times concentration of, let's say, A to the power of 1 if the concentration is molarity. So this is 1 if the concentration is molarity and K is 1/2, then 1/2 times molarity is going to give me this. You cancel the mole from each side, and then the value for K must be 1/2 in order to value or the unit for rate to become mole per second. So to get the unit for rate as a mole per second, the unit for A, what's coming from A, should be mole, not mole square, because this should be 1. So in order to get mole per second. So that's how we know the value for the unit for K for first order is per second, reciprocal second, or per second. So if the unit for K is given to you as a per second, right away you could say this reaction is a first order reaction. And if the reaction is first order reaction, then T1/2 equals 0.693 over K. What's happening in every half time? If the first half time, the concentration is going to be halved. Second half time, it would be halved again, which is 1/4 of the first. And the third half time is going to be 1/8 the concentration of the starting material. So every half time that it passes, the concentration is going to be divided by 2. So what is happening in second order reaction? When the A, it gives product, so A is one reactant. Let's assume that we have a reaction with only one reactant. Changing concentration of A over change in time, over the change in time is the rate. Negative sign means that this expression is based on the reactant. And then the rate law or general rate law for this reaction is rate equals K, concentration of A. If it's a second order, that's where this exponent of 2 is coming. So we have the constant and then concentration of A to the power of 2. So the change in concentration, so if this is basically the math part of this. So these two rates are the same rate. One is expressed based on the change in concentration, and the other one is based on the rate law. If these two, you make it equal, and because the rates are the same, so if the first side of the equation is the same, the second part of the equation is going to be the same. So when you have this equation and you rearrange it, you come up with this equation for second order reaction. So this is the equation for second order of the reaction. For second order reaction, you have this equation and it's simplified this way. The T half, when the concentration of A changes to half the concentration, you place A0 half here, and then you simplify it. You're going to get this equation for the half time. So at half time of the the half time for your second order reaction is going to be 1 over K initial concentration of your reactant. The unit for K, if it's a second order reaction, is going to be 1 over, so 1 over mass times second, I'm sorry, not mass, molarity times second. So molarity times second, this would be the unit for second order reaction. So unit for K for second order reaction. For zero order reaction rate, we write the equation into the rate law based on changing concentration, and it's also based on the general rate law, which is K concentration of A to the power of 0, and then the power of 0, this is going to be equal to 1, so rate equals to K. Okay, so rate equals K. What would be unit for K? If it's zero order reaction, the unit for K is the same unit as rate. So rate is mole per second, or change in molarity per second. This is going to be molarity per second. So capital M per second. This is the unit for K for zero order reaction. And the equation for zero order reaction, you have also the equation zero order reaction simplified. If you make these two equal and then you rearrange it. So basically the delta T is delta A, concentration A is K delta T, and then you're going to rearrange it in order to get simplified. Half time is going to be concentration of A at the 0 time over 2K. So you have two ways: either memorize this as a half time for zero order reaction, or know where it's coming from. Basically, when you have the equation for zero order, you put like A0 divided by 2 here, and then you rearrange the equation and come up with this formula. So, or memorize this as the half equation for half reaction. This summary, basically everything that we said so far regarding the first order, second order, and zero order, and basically what you need to memorize for the exam, or know how to come up with this equation. The rate law equals rate equals K, that's for zero order. That means it's independent from concentration of any of the reactants. So it only depends on the value for K. So concentration, it doesn't matter how you change the concentration of the reactant, the rate is not going to change. And you have the concentration time equation for each one of them. You are going to enables you to calculate the concentration at any given time. So if you have the time, you can calculate the concentration at any given time, because the initial value will be given to you often, or any of these variables that is missing, the other two must be given, or the other three must be given to you in order to find the missing one. So for first order, rate is the K times concentration of 1 to the power of 1. So the exponent here is 1. The only thing missing from this table, which you need to add for your notes, is the unit for K. So if you know the unit for K, then it's going to make it much easier for you to recognize, based on the information given for K, if this is a second order, first order, or the zero order. So for this one, unit for K is a molarity per second. For first order is going to be per second for K. Unit for K is going to be per second. And then you had for the second order is going to be 1 mole per second. Okay, 1 over mole per second. because 1 over mole per second is going to cancel with this in order to come up with the mole per second. So molarity over second, changing concentration over time, that's the unit for rate. And then what should be the unit for K, that if you multiply by m square, because concentration is going to be molarity, and then 2 means is a square. What should be for K, that if you multiply by this, it gives you this one. Okay, so it gives you this one. So that's how you come up with the unit for K. Exothermic reaction and endothermic reaction. For exothermic reaction, the value for EA, activation energy, which is the minimum amount of energy for any reactant to go to the product, and that is definition for activation energy. For exothermic, the reactant energy for the reactant is higher than energy of the product. This difference in energy between the reactant and product is given off the environment. That's why it's exothermic reaction. For endothermic is opposite. Your reactants, they have less energy, they gain energy, and they change the product. So product have more energy, and this amount of energy is being absorbed by your reactant to change to the product. Which reaction is slower? The higher activation energy, the slower the reaction. Smaller value for activation energy, faster the reaction. That's the one thing. And then the other thing, if your reaction has more than one step, that has slow step and fast step, the rate determining step would be the step that is a slow step. A slow step is going to determine the rate of the reaction, because the fast reaction is going to happen anyway. Remember I said the rate constant is going to stay constant as long as you don't change the temperature, but if you do change the temperature, then the rate constant is going to change. This is a given value, and then you have the EA is the activation energy, so it depends on the activation energy, how significant is the change in temperature, change in rate of the reaction. Basically, if it's an endothermic type reaction, you increase the temperature, the reaction is going to be much faster. So it's going to be the reverse effect. So the time concentration, or the temperature, and the rate value for the rate, you have this equation is known as the Arrhenius equation. And sometimes if you have the value for K, and you want to find a different, you have the activation energy and you want to find the value for K at different temperature, it gives you, you can use this formula, the Arrhenius equation. If you plot the graph, you use this for one of your experiment in 1046. If you're doing experiments at Central Campus, if you have the temperature that you performed experiment at different temperature, so you have the value of temperature, this must be in Kelvin, and then you have the corresponding value for K, and you get the natural log of K to get the point values. You plot the graph, the slope of the graph, when you calculate the slope, basically the delta y over delta x, or rise over run, that value is the A over R. And then this negative is going to basically be canceled by this negative slope because it's decreasing. So you have you can calculate the value for EA also experimentally. All you have to do is to get the rate of the reaction, find the rate for the reaction at different temperature, and then from the rate law of that reaction, you find the value for K at different temperature, you get the natural log for K at different temperature, and then you plot the graph, and experimentally you can calculate the activation energy. So reaction mechanism, basically like studying of reaction step by step. In order to find out if the reaction, your reaction, it happens in one step or two steps, this study is coming from like physical chemist. A physical chemist is going to study this. Basically, they monitor what type of species they are. They exist in the reaction mixture from the start point to the end point of action. So they have to have like some evidences, or based on the structure formula or the energy diagram, they can decide if this reaction is taking place in one step or two step. You don't have to basically know the mechanism. What is the mechanism for reaction? But what you need to know, if you know reaction is two-step reaction, to recognize which one is a slow step. Basically, that's the one with the larger value for EA, or activation energy, and that is the one that determines the rate for the reaction. So when you have like a rate determining step for a reaction, you could have you can have a unimolecular, you could have bimolecular, or teramolecular, when you have like three molecules involved in rate determining step, or one molecule is involved in the rate determining step, then you could say like a unimolecular. For a reaction that is a first order reaction equals K concentration of A, this is a unimolecular step, or your rate determining step is a unimolecular reaction. So it's only one molecule involved in the rate determining step. If you have a reaction that has a rate law of K concentration of A concentration of B, this is the example for bimolecular. So if you have bimolecular, that means two molecules are involved in rate determining step of this reaction. Unimolecular, and then you have bimolecular. You have a bimolecular, but it's the same molecule. Okay, second order basically. Okay, second order. If you have multi-step reaction, when you add them all together, it should come up with the overall balanced equation. And the rate determining step is the step that is going to be determined, again, experimentally, because all you have to say, is it only A affecting the rate of the reaction? That means your rate determining step involves only compound A. And is it both A and B? Or what is the major factor, or more, which one has more significant effect in the rate of the reaction? And then you look at the different step of the reaction to find out if that appears in that step of the reaction or not, and look for the slow step of the reaction also. Basically, you are going to apply the application, or know the definitions and application of the mechanism into the rate law. So if the mechanism suggests like 2-3 steps, then you determine which one has the highest activation energy. Or if you are given the rate law for reaction, then you could see which reactants are involved in that rate determining step, then others are not rate determining, or others are fast step of the reaction. So if you have these two steps of the reaction, then these are given. If this is given to you, and then you're given a rate law, the only step, the only molecule or the compound, this is like a bimolecular, but it's coming from the same molecule. Okay, this molecule is involved in the rate determining step. That means this part of the reaction, because it's only we are looking at the reactants, is not involved in rate determining step. So is going to make it this step to be the rate determining step, and this step is going to be the slow step of the reaction. So this step is going to be fast, this is going to be slow. The intermediate that is forming, NO3, is formed here in the first step, is consumed in the second step, that gives you the final product, but that's not involved in the rate determining step, is not in the reactant site for the slow step of the reaction. So basically being able to answer questions in this nature using the different steps of the reaction. We have two-step reaction here, comparing two energy diagram when there is a catalyst, when there is no catalyst. So basically, when you add the catalyst is going to change the mechanism of reaction. Maybe it drops to like two steps, or changes to two-step reaction instead of the one-step reaction. And then what it does, lowers the activation energy. Lower activation energy, faster reaction. So basically that's how catalyst works. It changes the activation energy in order to make the reaction faster. The different type of catalyst that you could use like acid or base catalyst. So basically in any catalyst is something that is not going to be consumed in the reaction. It can be consumed in step 1 and produced in step 2 of the reaction. So if the H+ is needed for the first reaction, and then in the second reaction is going to be produced, so it's consumed here, produced in the second reaction. This means your H+ is only catalyst. In the overall reaction is not going to appear, but is needed for the reaction to initiate, to start the reaction. So heterogeneous catalysts, they can be like a solid catalyst. So the reaction takes place at the surface of the solid catalyst, or you could have like homogeneous, like acid or base that is coming into the solution. This is like a heterogeneous catalyst, that reaction takes place at the surface, and then for homogeneous you would use the same phase. Enzymes are also a catalyst that makes the reaction actually to be, it basically changes the route for the reaction, or this is the general, this is saying what enzyme does to your reaction. And going through this like larger value EA is going to break down to 2 smaller steps, and then this value for EA is much smaller than the one with before the catalyst or without the catalyst. So as a result, faster reaction. Okay, the overall or overview of the kinetic was presented here. I had to record it in like 2 steps. I just hope that the first step is also recorded for you. I'm going to post it in an announcement, so we are not going to actually have a meeting at class time for today.